if you actually see something in isolation, and you see a signal in the infrared or the ultraviolet, you really cannot tell, unless LIGO tells you, you know what, I have seen this signal. This signal combines or implies the merger of two objects of these masses, and based on what you know in the masses, then you can go at the electromagnetic counterpart and tell apart whether it was from one equation state or another. And this kind of underscore what I find exciting about this field. It is not what we have thought of, but what might happen. And so far, different people in the different camps have been thinking pretty much in isolation. The GR people have been thinking GR-minded questions, the astrophysicists, astrophysics-minded question. But it's the combination of the multiple disciplines that actually gets to be fun. I mean, as I went through the talk, I threw out input from particle physicists where they are trying to use these systems to try to explain where dark matter could be described by a light massive scatter in the universe, or the populations of these binaries. If there are enough binary black holes sharply picked, other people have predicted that maybe they can actually, the black holes themselves can be the primordial population that actually explains dark matter. But the point is, gravity waves have become now this kind of fountain of wealth of knowledge that people should come and contribute it to, because the most interesting things are what's coming. And we have just one detection. We're going to have to see what happens in the future. But for a long time, we've been putting a lot of effort to try to detect gravitational waves. Now is the time to see what the gravitational waves can do for us. Thank you.
Since the first discovery, how many more gravitational waves have been detected?
You're asking a question that I don't know the answer of. I know rumors.
Okay.
So the gravitational, the observation had two systems, right? So one was the D detection. Now it's actually scary to think that we in the gravitational, in the general relativity camp, we're talking about things that have weird names like GW150914. This was used to be kind of astro people crazy enough to have these kind of license plate numbers. But now we have one. Then there was another one called LVT something or other. And LVT stands for LIGO Virgo trigger. So that was a signal. I mean, we can have it here. Right, so if you see the brown square, the rightmost brown square, which is not the crazy one, so that was the LVT something or other. So that could be a detection. The thing is that it has a sigma of 2 point something. So it's not enough to claim a detection. People in particle physics know this very well. But that might be a detection. Then there are rumors of a few more, but I don't know. We should know in 3 weeks or so.
Another question. Regarding the spin-to-graviton Weinberg linear gravity, you mentioned something. What is that?
Say again?
You were saying Weinberg theorem says, it's in his book, if you have spin-to-graviton and diffeomorphism, then Einstein field equations should be linear?
No. So if you ask for a theory that mediates gravity with a spin-2 massless field, and respective diffeomorphism invariant, then and you're in 3 + 1 dimensions, then you obtain linearized answers to the question. That still doesn't say that the very nonlinear regime, we know what it is. So there is, well, people use their different biases about if you know what the linear theory is, then you should know that the full theory would be GR, but this is where things can deviate from it. You can imagine that now, so you also imagine that your theory, if you actually, in addition, impose that there is no intrinsic scale, preferred scale, then it's hard to see how you're not going to land in general relativity because, well, you just take the limit. But now if you say, well, there is an intrinsic scale, and beyond some particular scale, things behave one way and passive behave in a different way, then you can imagine going from linearized equation to something else. And these theories that violate the strong equivalence principle are, well, not in that because we added something in, or you have added something else. But they are like that. There's a scale in the system that has to do with the binding energy of the object if it is non-vacuum, because there is a coupling between matter and the scalar field. And above some binding energy, then you scalarize, and now you endow this object with an extra hair, which is a scalar hair.
I want to compare the gravitational wave discovery with the discoveries in particle physics, like Higgs boson.
Yeah.
So apart from the need of having a known statistical significance bigger than 5 sigma, we need to be sure that the systematic errors are not present. And some systematic errors are, lie behind the technology. In the case of the Higgs boson, we have two different experiments, CMS and Atlas, seeing the same thing. But as far as I know, in this case, there is no any other experiment with a different technology that has observed the same event. So how can people say that this is a discovery?
Well, first, let me go back to the Higgs, because actually I was asked this question 2 weeks ago, and I was in Pitt, and they asked me this. So the particle physics, and I have no problem saying it, because I got asked the question to particle physics friends. Where you go, if you had money to put from your pocket into the discovery of Higgs or the discovery of gravitational waves, where would you have put it? I think the answer is absolutely the case that it's gravitational waves. The Higgs, you can win or you can lose. And I think we have lost to some degree with Higgs. So it could have been exactly what you have predicted with the standard model, but it could have been something else. If it was something else, then there's a whole bunch of things you can do. This was almost exactly, so there's a little bit of tension, but you can actually make it work. And so people discover the Higgs and then what? Now with gravitational waves, you can do two things, but let me not even talk about gravitational waves. Let's go to Eddington's mission to detect the bending of light here that's close to Brazil and Africa. Two things that could have happened that day. Something completely different from general relativity, and then you go and try to get a new theory. Or something exactly like general relativity, and then you have lensing. And we have used lensing for discovering dark matter, planets. So it's a win-win situation. So now to your question. It is true that CMS and Atlas are different. But these guys, you only have seen kind of the surface of the kind of things they've done. Remember, they've done all these are a set of analysis where they inject fake signals and they try to get them. They have independent, the CBC and this coincidence wavelength analysis and the data analysis are completely different. One uses theory, the other says, I don't have any theory. So the only thing you could do, the other thing they do is you have to check what they know. So what else could have happened? That's the question. Maybe there was some artifact in the detector that made it bring us in this way. So one of the things they do is they you have two detectors that are separated from each other. You say, I have a signal here, and within the light, bounded by the light travel time from a gravitational wave to move the speed of light from one detector to another one, you had another detection here within this time. So now shift all this data so there could be no coincidence between one detector and the other, right? Because you shifted by more than one that amount. And then you cross-correlate again. And then this curve in here is the amount of fake detections. What is the chance of a complete fluke in the detector which have given you something that looks like the signal that you're seeing in one of the detectors? And this is what you get. And the signal is over there. So at this level of that signal, the fluke, the statistical possibility that something that looks like a gravitational wave would have shown up that would have given you confidence is not even in the plot. It's down here. The difference between this line and that line is now the following. You take the same signal that you have, you subtract the gravitational wave that you think now you have, and then you do the same exercise. And look how this falls. And this one is right here. So this means, now translated into numbers, that the statistical probability that this signal would have been coincidence in the two detectors as a result of a fluke is over 210,000 years. So yes, it would still be a fluke. So could be the Higgs. The analysis has been so thorough here. And remember, this is not in isolation. You also have the Hall's and Taylor binary Pulsar that gives you an expectation. But this on its own really stands out. If you had been a signal-to-noise age, yeah, but this was fully full. This was ridiculous. I mean, in hindsight, of course, you can explain is, well, if you're going to see the first signal, you'll be the loudest one. So in some sense, you were already selectionally biased to see the loudest one, and this was a posteriori, not too unexpected. But the amount of effort that has gone here is just amazing. So, yeah, I think it's done as strongly as the discovery of Higgs. And with better possibilities of doing interesting physics afterwards.
I will make first a short comment. I mean, the question I think was that there were two detectors. In this case, were also two detectors. So,
right, but it's the same, but doing the same analysis. But I mean,
yeah,
right.
but it's two detectors, and the coincidence was at the right time. I mean, so this is not just a chance.
The other things that let me just add to that, well, it's absolutely right. There is also, in order to have this previous curve, in order to have one and the other one match, they have to do two things: shift in time and actually flip in sign. Because one detector is like this and the other one is like that. So they also agreed on that. So you have tons of numbers, but go on.
Yeah. So my question is related to the angular momentum stuff. If I remember correctly, I also took the data of numerical relativity, and they put spin in their calculation, and I think they were not aligned. So can you comment more on this stuff?
Right. So the question that Waterloo is asking, the binary templates. So let me backtrack a little bit. So because I said the following, we have the ability to produce a template, and I stand by that claim. But every template is expensive. So in the case of binary black holes, constructing template is easier because there is only one parameter, or well, two, the mass and spin, and then, well, how do you orient it? With the neutron star, in addition, you have to worry about the equation of state itself. And any of these things are expensive. So while in principle, if you tell me tomorrow, I know for a fact, because God just told me that the parameters of the systems are so, then within a month, you're going to get your waveforms perfectly fine. But if you don't know, then you have to construct and then go through this analysis and then try to see which one of the members of the template maximizes the inner product. So what Osvaldo is referring to is, as far as spin is concerned, these templates or these theoretical info that go in that inner product over there either have no spin or have spin that are aligned with the orbital momentum. So they could be like this or like that. But they don't have any arbitrary orientation. Arbitrary orientations will introduce some spin orbit coupling that actually will introduce some modulation. But it wouldn't have been detected in such a short signal, which is unfortunate. Eventually, we'd like to do that. So now they did the analysis. And they can do the analysis in three ways. They can just restrict the analysis to the pre-merger. And if they do that, they have a whole slew of possible spin. They're on the low end side, but it could go 0.4, 0.5 or so. If they only analyze the after-merger stuff, how fast the black hole is coming out, then you have something else. And then if you combine both of them, then you have a smaller region. And that's how the final spin comes out to be 0.67. But if you ask the question, now, from the point of view of what was the binary doing, if I believe the 0.67 with those errors, how could I have constructed this from the binary that was coming together? Then, well, either I have low spins to begin with, or they were amply aligned, but we know that's unstable. So the only option I have is that they were low to begin with. And they comment on this.
This so low speed, it's still a problem if there is a black hole at primordial one, like some people say. Or in this case, the low speed would be not really a problem.
I don't think that's a problem. It doesn't. I mean, so people thinking of primordial black holes and discovering dark matter, I don't think they have worried too much about spins, just because that's like a second order effect. You need the masses, and the only thing they worry about is what the bounds of the masses are, because if they are too small or too big, then you would have had other observable consequences in data.
I would just mean if this is to ask primordial one, then they should have a small speed or not?
I As far as I know, I mean, I don't know. And I would be surprised that people have arguments claiming that primordial black holes have any spin, any particular spin. Yeah, so, but I don't know the answer to that question.
I have a question regarding this plot. So, as you said, maybe soon we know if there are more detections and that it was not just published. But the way it is, it looks a little bit weird because one I think maybe they would expect that for each 5 sigma signal, I should have many more 3 sigma, 4 sigma, 2 sigma and a half signal. Right? So, what's besides the fact that they just didn't publish, what's the possible explanation from this? Just selection effects? You don't see that in your data?
No, because it's, as you said, if you have the 5 sigma sitting at 400 megaparsec, this was 24 SNR, when that thing in the end was called signal to noise ratio. So, and as I said, you could put them 3 times further out, and you would have seen exactly the same system with a sigma, with an SNR of 8, and you would have moved to the left on that plot. So, because that plot doesn't say anything about the physical characteristics of the object, just the relevance of that particular event. So, it's interesting. So, they had that one and the other, this one that we call it the LBT. So, if you were to kind of just by bias say, okay, that's also a signal. Well, now it's consistent with what you're saying. This is a similar system, further out, and that's fine.
But theoretically, I mean, you expect this that exactly goes like the power law or something that you have, many more 4 sigma and a little less 5, a little less 6 in the future with more data.
With more data, right? Because then you're going to be, but it again depends on the distribution in masses of these objects and where they are. So with only one signal we cannot say, but I mean your point is exactly right. What they're going to come up with in 2-3 weeks, that would be need to actually fill in this plot and tell us where this was. Because it couldn't have been a lucky event, right? We didn't have to be democratic. But if it was democratic, then you expect this one to begin to have more signals there.
Just continue on that line. If it was democratic evidence, then and it is such a strong evidence, shouldn't it have been attacked before the previous rounds?
That's an excellent question. And the answer is yes, but. The problem with the but is that LIGO did 2 things when they improved this one. It went down in sensitivity, and that doesn't matter because the sensitivity went up by this time, or it went down by this time, was a factor of 3. So the 24 now was an 8 then. But it also did this in frequency. Well, depending on how you see it, this in frequency. Because before the frequency was, the bound on the frequency was at a higher one, you actually would have seen maybe the last piece, and you didn't build enough signal to noise. Right? So because when we say 24 divided by 3 is 8, you would have seen it. That assumes that you actually saw the whole thing and you were able to accumulate all the signal to noise. But if you actually concentrate on the last few cycles, then you don't get it. So you lost it. But yeah, that was very relevant. That was the first question. Why didn't you see that before? And that was the answer.
Just the last question. Now about polarization. How many more detectors you need?
Oh.
See polarization.
That's a good question, and you actually need one. The problem, remember they would say this thing that one is with respect to the other one, because it was built in such a way that you could actually do this test as opposed to like another blind test if they were measuring the same polarization and one with respect to the other. But Virgo is not one. So the moment you have Virgo on, now you can begin asking polarization. And India is still not known. Still, India, people are beginning to talk of maybe 2024 now. But Kagra should be on earlier.
Questions?